How's it going, everyone? In today's video, we're going to learn about Python's three main approaches to concurrency: threading, multiprocessing, and AsyncIO. Each one has its own use case, and understanding when to use which is crucial for writing efficient Python code. We'll start with a simple synchronous baseline. This is how you'd normally write code that does multiple tasks. Then we'll see how threading, multiprocessing, and AsyncIO can help us speed things up. The key is understanding the difference between IO-bound tasks, like network requests or file operations, and CPU-bound tasks, like heavy calculations. Before we dive into the different approaches, I just want to mention that I'll be using Z, the IDE, throughout this tutorial. If you'd like to follow along with the same editor, you can find the download link in the video description below. Let's start with a simple example that simulates some work. We'll create a function that takes some time to complete, and then we'll run it multiple times synchronously to establish the baseline. So for this example, we're going to import time, and then we're going to create a simple function that simulates some work. This could represent anything: a network request, a file operation, or a calculation. For now, we'll just make it sleep for a short time to simulate work being done. So inside this block, we're going to make the function sleep, and we're going to return that the task was completed. Next, we'll run multiple tasks sequentially. And to do that, we're going to create a function called runSync. And the body is going to look like this. And this is the synchronous approach. We do one task, wait for it to finish, then do the next one. This is simple and straightforward, but it can be slow if we have many tasks that could potentially run at the same time. So here we have for I in range tasks, the result will be the result of the work, and then we will append the result to the results. Again, this can take a lot of time since we have to wait for this each time before we append it to the list of results. Anyway, let's run our synchronous tasks and measure how long it takes. So here I'm going to create the if name is equal to main check. I'm going to use a start time, grab the results, and then grab the elapsed time. Then I'm going to print the synchronous results, and for result in results, we're going to print the result. Here we have the total time it took and the note on how synchronous execution works. So right now, if we were to run this, you should notice that it took 0.52 seconds to run. Now let's see how threading can help us speed up our code. Threading is perfect for IO-bound tasks, things like network requests, file operations, or waiting for external resources. The main idea is that while one thread is waiting for IO, other threads are free to continue doing work. Python's global interpreter lock, the GIL, means that threads can't truly run Python code in parallel. However, when a thread is waiting for IO, it releases the GIL, allowing other threads to run. This makes threading great for IO-bound tasks, but not so great for CPU-bound tasks. In the next example, we'll be using the thread pool executor from the concurrent futures module. This is a modern, clean way to work with threads in Python. It handles all the thread management for us, and it's much easier to use than the older threading module directly. So, at the top of our file, we're going to import thread pool executor and as completed from concurrent.futures. And nothing's going to change with this function. But now instead of using the runSync function, we're going to change this to run threading. And I forgot to mention, but in this example, you should imagine that this is simulating an IO-bound task, something that spends time waiting rather than computing. So if you made an API request and you're waiting for that request to finish, we could pretend it's simulating that. But inside the run threading function, we're going to create some results. And with the thread pool executor, we're going to set the max workers to the max workers as the executor. Then we're going to create a variable called futures, which will equal a list comprehension. And here we're going to submit the work with I and 0.1 for I in range of tasks. Then below, we're going to grab the results as they complete and append it to the list of results. And finally, outside the with block, we want to return the results. And personally, I really like thread pool executor because it's clean and handles all the thread management automatically. The context manager ensures that threads are properly cleaned up when we're done. The asCompleted function gives us results as they finish, which is nice for showing progress or handling results in order of completion. The key thing to remember is that threading is great for I/O-bound tasks because threads can wait for I/O simultaneously. But for CPU-bound tasks, you'll want to use multiprocessing instead, which we'll see next. But before we do anything, let's fix the code inside the if name is equal to main check to see how long this takes to run. So here we can type in run, and I don't even remember what the function was called, run threading. I have a goldfish memory. And the note should be replaced by this. Tasks ran concurrently using threads. Now when we run this, what you should notice is that the execution was much faster, because we did not need to wait for each task to complete before moving on to the next one. Next, let's talk about multiprocessing. Unlike threading, multiprocessing creates separate Python processes, each with its own memory space and Python interpreter. This means they can truly run in parallel, even for CPU-bound tasks, because each process has its own GIL. Multiprocessing is perfect for CPU-bound tasks, things like heavy calculations, data processing, or anything that uses a lot of CPU time. The trade-off is that it uses more memory and has more overhead than threading, but for CPU-bound work, it's the way to go. For this example, we will be using Process Pool Executor instead of Thread Pool Executor, which provides the same clean interface as Thread Pool Executor, but uses processes instead of threads. This makes it easy to switch between threading and multiprocessing depending on your use case. Now we're going to remove all of this, because here we need to create a function called doCPUWork, which is a CPU-bound task, something that does actual computation rather than just waiting. This simulates the kind of work that benefits from multiprocessing. And this is the code we'll be using for this function. All it does is loop through a range of iterations and multiply that iteration by itself. Then it appends it to the result. Down below, let's create a function called runMultiprocessing. And here we're going to set tasks to 5 and max workers to 5. Then as always, we're going to create a list of results, and with Process Pool Executor as executor, we're going to add another list comprehension. And just like before, we're going to collect the results as they complete. And at the bottom, we're going to return the results. And once again, the key difference from threading is that each process has its own memory space. This means you can't easily share variables between processes. You need to use special mechanisms like queues or shared memory. But the benefit is true parallelism for CPU-bound tasks. And my recommendation is that you should use multiprocessing for CPU-bound tasks and threading for I/O-bound tasks. If you're not sure, think about whether your task spends more time waiting or computing. That will guide you to the right choice. But now let's see how long it takes to run multiprocessing. So here we will run multiprocessing with 5 tasks and a max of 5 workers. And it looks like I forgot to change this for threading earlier. So on the previous example, this should have read threading. But this time I'm not going to forget because I'm just going to delete it entirely and paste in the correct code. So here we're going to print multiprocessing results, print all the results, the total time it took, and the sexy note that the tasks ran in parallel using separate processes. Now when we run this, you should notice that it finished quite fast, because we were able to run all of these tasks at the exact same time. If we were to run this function synchronously, it would take much longer, because it would have to run the function, wait for the result, run it again, wait for that result, and do that 5 times, instead of running it 5 times at the exact same time. And finally, let's look at AsyncIO, Python's modern approach to asynchronous programming. AsyncIO is perfect for I/O-bound tasks, just like threading, but it uses a different model. Instead of threads, it uses a single thread with an event loop that manages multiple coroutines. The key advantage of AsyncIO is that it's more efficient than threading for I/O-bound tasks. It doesn't have the overhead of creating and managing threads, and it can handle thousands of concurrent operations with minimal resource usage. The trade-off is that you need to use async await syntax and work with async libraries. And AsyncIO is great for things like web scraping, API calls, or any scenario where you're waiting on network I/O. It's become the standard for modern Python web frameworks and libraries. My recommendation is to use AsyncIO for new I/O-bound code. It's more modern and efficient than threading for most use cases. Now to use it, all we need to do is import AsyncIO. Then we're going to create a function called doAsyncWork. Note that here I had to use the async keyword to create an asynchronous function. And instead of using time.sleep, here we use AsyncIO.sleep, which is non-blocking and allows other coroutines to run while we're waiting. Then at the bottom, we should return that the task was completed. Next, let's run multiple async tasks concurrently. So here we're going to create a task list for all the tasks, and we're going to use AsyncIO.gather to run all tasks at the same time. The event loop manages switching between them, so while one task is waiting for I/O, others can run. Then we're going to return the list of the results. And personally, I really like AsyncIO because the code is clean and readable. The async await syntax makes it clear what's asynchronous, and AsyncIO.gather is a simple way to run multiple tasks concurrently. The event loop handles all the complexity of managing coroutines for us. The key thing to remember is that AsyncIO is single-threaded, so it's great for I/O-bound tasks, but not for CPU-bound tasks. For CPU-bound work, you still need to use multiprocessing. But for I/O-bound tasks, AsyncIO is often the best choice because it's more efficient and scalable than threading, with the caveat being that you need to use async await syntax and work with async libraries. But next, let's time it and see how long it takes. So we're going to create start time, which will equal a performance counter. Then we need to call AsyncIO.run to grab the results. And at the bottom, we'll grab the elapsed time, which will equal time.performanceCounter minus the start time. And below, we will print AsyncIO results, the total time it took, and another note that says tasks ran concurrently using AsyncIO. And now when we run this, what you should notice is that it was able to complete the task incredibly quick, because each task did not need to wait for the other tasks to complete. We could start them all at what felt like the exact same time. So, just to sum it up, threading is good for I/O-bound tasks. It uses threads, but is limited by the GIL. Multiprocessing is best for CPU-bound tasks. It uses processes and achieves true parallelism. And AsyncIO is best for I/O-bound tasks, and is the most efficient for modern I/O-bound tasks, when you want fine-grained control over the concurrency. And if you need to choose, you should choose based on your task type. If it's I/O-bound, use AsyncIO or threading. Otherwise, if it's CPU-bound, use multiprocessing. But that just about sums up everything I wanted to talk about in today's video. Do let me know in the comment section down below whether you have any more questions regarding AsyncIO, multiprocessing, or threading, and I'll do my best to answer. But otherwise, with all that being said, as always, thanks for watching, and I'll see you in the next video.